get at this here. So a radio station on Earth's surface emits a sinusoidal wave. So if we just thought of, well, let me first, so here's some transmitter, okay, on the ground on Earth, okay? And then out in space somewhere, we would have some satellite, okay? And so that means there'd be some distance r between those two things. And so this transmitter, in an ideal situation, you know, perfect antenna, the surface of the Earth, and all sorts of stuff, we would actually have essentially a kind of a hemisphere, okay, of kind of the distribution of the intensity of the situation, all right? And so that's just sort of picturing the way that the wave intensities would beam out, if you will. Okay, now of course nothing's perfect, and those of you going into electrical engineering and specializing in antenna design, you can have a whole specialty in just that. Go get PhDs on just that topic and whatnot. All right, it's that big a deal. So, kind of reviewing, you know, we already know that you know, intensity is power per unit area, okay? And in this case, the area that we're dealing with will be half the area of a sphere because it's a hemisphere, all right? So instead of 4 pi r squared, it'll be 2 pi r squared. So 2 pi, and if we're dealing with something that's 100 kilometers from the antenna, then that's going to be 10 to the 5th meters. And so this is going to be, that's getting squared. This is going to be 6.28 times 10 to the 10th meters squared. That's the surface area over which that power is intensified. So while that's a simple formula, understanding what the formula refers to. Intensity is power per unit area. What area? Well, at 100 kilometers, the dome of this radially expanding thing in all directions is going to do that. All right, so we have that going for us. So the intensity should just be the 50 kilowatts, 50 times 10 to the 3 watts over this extremely large area. And we'll get 7.96 times 10 to the minus 7 watts per meter squared. So we have our intensity, and why do we need that intensity? Well, if we're going to get to the amplitudes of the fields, then we need to recall that intensity is the average of the pointing vector, which has a form, if we think back to the other day, of the electric field squared over 2 mu naught c, magnetic permeability constant, speed of light. So this means that our max electric field strength, or amplitude, the peak of one of those waves would be that. Well, this thing right here, this is the average pointing vector. It's because it's the intensity, All right. So Emacs, do some plugging and chugging. 4 pi times 10 to the minus 7 and a bunch of units. 3 times 10 to the 8th meters per second squared. I'll leave the units out since I'm running out of space here. And then this number we just, obtained above. All right?
3 times 10 to the 8.
Yes, speed of light. So this is mu naught. This is speed of light. And that's the S average. And so this works out to be a really small electric field strength. 2.45 times 10 to the minus 2 volts per meter. So fractions, 0.2 millivolts per meter, I guess. Something like that. Or, I'm sorry, 24 millivolts. 25 millivolts. So there we have the electric field strength right there. And given that E over B equals C, this is one of the things that we found along the way through Maxwell. That means that my B max will just be E max over C. So divide the number I just got by 3 times 10 to the 8. And I get 8.17 times 10 to the minus 11 Tesla, which is an insanely small magnetic field strength. But the electric field strength was also really small. So these are the kind of mathematical maneuvers you'll go through, small set of formulas that shake out of our equation set. Okay. More satellite stuff, because that's really practical, obvious. Somebody gets paid a lot of money to make these things work out nicely. So some satellite has solar panels, 4 square meters of solar panels. That's not a lot. A lot for a satellite. But if the sun's radiation is perpendicular to the panels and is completely absorbed, then find the average solar power absorbed and the average radiation pressure. So let's remember that we have this, I is power per unit area, or power is intensity times the area. So we can get straight to the power through our intensity formula. All right, and so the intensity. Now, here's the thing. The intensity of radiation right before it enters the atmosphere, which is where a satellite's going to be, there's a known value that I didn't type into the thing. So the intensity is actually 1.4 times 10 to the third watts per meter squared. And so this number here is intensity of sunlight just above atmosphere. So it's something we would look up in a table. It's a known value, right? So that's sort of a giveaway, and then we know the other value, 4 square meters. So in one sense, this is a really easy part of this problem. And this problem's relatively simple if you have the formula set. So you get 5.6 times 10 to the third watts, or 5.6 kilowatts would be the power that could be absorbed there. So that's a lot of 5 or 6 kilowatts. You know, how many cell phones could you charge with that? So that's how these things, you know, you get a small solar array for a satellite and it'll run those computers. So charge up, run for a while, put them away, come back, do its stuff. So that's average solar power absorbed. That's done there. And then we have this formula we derived the other day that the radiation pressure, it's supposed to be a lowercase p. All right. This is also a known value. I think I meant to say put the find the force of the radiation, but I wrote average radiation pressure, so I'll have to. Anyways, there is a known radiation pressure if we know it right up at the surface. If we know the power rating there, then we know the radiation pressure, and so this is. So folks that work in this field and deal with these things, there's a bunch of numbers that they just come to know. And they're known constants that plop into the computational lap, so to speak, and makes things easier. What I really wanted to mess with here was I want to know the force of that radiation pressure, which is just going to be, since pressure is force per unit area, the force is going to be that radiation pressure times area, which is going to be this number we just pretended to look up from some table somewhere, times that area. So this problem is a simple problem if you know the formulas, because you look up one value and you're given the other. And so the force, the force of this radiation, 1.9 times 10 to the minus 5th newtons. So 20 millinewtons, if you will, 19 millinewtons, 19 millionths of a newton. So not a lot of force hitting it, which is good, because that would slow it down if it was a lot, but we get a lot of bang for the buck on a solar panel. Okay? But it is being beat up lots of times per second. So from a material science standpoint, well, you know, if you leave something out in the sun long enough, eventually it deteriorates and you have to replace it. Why is that? Well, it's because it's literally getting beat up. It's tiny little blows, but it's gazillions of them per second for a very long time. Hence, the sun literally beats things down. So it's a simple example. A material scientist would actually sum up forces like this and say the end of life for this panel, given that it's made out of silicon and germanium or whatever it's made out of, is going to be X number of years. So we would expect this satellite to stop functioning well, or the power grid will start to be less than it should be. Or well, I would expect a catastrophic failure, it should crack or something, because it's going through major temperature swings. Really hot, really cold, really hot, really cold. It's being mechanically vibrated, it's going at a really large speed. There's all these things that you would add up, and that would factor into how long is this thing going to last. And so that means we collect data for this long on it, and then we replace it. So we have 10 years to get the money to make another satellite and get it up in the air, so to speak. These are all things that a company who engineers and makes these things would have to consider, from how long the solar panel lasts to how long the hull of the ship lasts, and you'd try to get things so that they have the same end of life. Otherwise, you're wasting money. Okay? Yeah, right, that'll happen. A green laser pointer, which I mistakenly took back to my office. I actually have, oh no, I didn't. Has a power of 1 milliwatt. Yay. You shine the laser pointer perpendicular to a white piece of paper which reflects the light. The spot of light on the paper is 2 millimeters in diameter. This one tends to shine something about 3 millimeters, but all right. What force does the light from the laser pointer exert on the paper? Because it will exert a force on it. So let's go back to this thing here. We have intensity is power per unit area. We've been given a power rating of 1 milliwatt. The area is going to be pi r squared, and the radius, if it has a 2 millimeter diameter, it's got a 1 millimeter radius, or 10 to the minus 3 meters squared. Do the crunching on that, and you should get 318 watts per meter squared. Yay. What force does the light from the laser pointer exert on the paper? So this radiation pressure is going to be force per unit area. But radiation pressure was also for a reflective surface. Remember, it was double of the intensity per speed of light. We worked that out on Monday in the last lecture. So basically, this means that the force, if we just solve for force, we'll get double the area intensity per speed of light. So 2 times pi times 10 to the minus 3 meters squared, just like we did before, and 318 watts per meter squared, and 3 times 10 to the 8 meters per second. So the force here will be a whopping Antichrist number of newtons. The devil is responsible for beating up this piece of paper. All right. So there's this 6 trillionths of a newton, 6-7 trillionths of a newton force banging up against this piece of paper. And so just as a did we talk about the optical tweezing of DNA? Did we
said something about it.
But we didn't walk through the papers. We're going to do that soon. It happens to be that your DNA, this molecule, is shaped like a spring and actually has a spring constant. It's about, I want to say it's I think it's half a piconewton per nanometer. And somewhere in the range of 20 to 60 piconewtons is the range over which you can functionally stretch that molecule. Outside of that range, you either don't stretch it or you tear it apart. You melt it, which is, I think, the lingo they use in biology. So we have machines that measure that. We have machines that can do it, that can stretch a DNA molecule with piconewton force style. So, interestingly, this mini lightsaber, okay, sort of, it doesn't stop. This exerts the same level of force that would spring a DNA molecule. This is a kind of an energy source that would be required cellularly to start to stretch a DNA molecule. Okay, why would that matter? Frame of reference for just understanding you know, what's a device that's comparable to what's these molecular machines inside? And perhaps that knowledge might be material in making something like a syringe on a chip, which they've made. They got things that can just little microscopic sized chips, and they put them in you and it goes and does stuff. All right? I would say in the next 10 to 20 years, you'll start to see where they can just shoot a little thing into you. It'll go find the cancer or the liver dysfunction or the whatever and just fix it. All right? All right, meanwhile, back at the wrench. So that's it. This problem in the bag. Another green laser pointer problem. Same situation. What's the amplitude of the electric field in the laser beam? Well, we already know that the intensity is 318 watts per meter squared from the last problem. And we're told one of our equations, or the way that it shakes out, if we take that one of our equations we worked out on the last lecture, there's this equation. If you squared both sides, you'd have, this is for a reflecting surface, it's just 2I per C equals the square of that field. And so we do the plugging and chugging. 2 times 318, I'll leave the units off for, because they won't matter. That's 8.85 to 10 minus 12, so the electric field amplitude ends up being 489.7 volts per meter. That's a pretty intense electric field. So this thing shining down on a piece of paper, the amplitude of that electric field is hundreds of volts per meter. Next problem. More space stuff. Low-cost way of sending spacecraft to other planets is with solar sails, which we're just pretending that we can do this. We have some material technologies to advance and some manufacturing things to advance before we can really successfully build a solar sail. But if we could build it, it would get us there. Okay, it works for Count Dooku, so anyways. Those of you that are Star Wars fans. Meanwhile, back to the ranch. What was this problem? It's using radiation pressure from the sun. So the intensity. So that's the beauty here. We've already determined you've felt the radiation pressure of the sun, which means it exerts a force on you. We've computed many times that it exerts a force. So that means you could use the sun to sail away from the sun. If you could catch those zoomies, enough of them to fill your solar sail, and then it would push you away. If you could collect up enough, big enough sail, it'll overcome gravity and poof, you're on your way. And it'll keep accelerating you until your ship flies apart or you run into something. All right. What size sail is needed to get to Mars at an acceleration of 1/100th of a meter per second, which will add up over the very long journey and get you to a nice speed? Well, I forgot to mention mass of ship. Assume mass of ship is 10,000 kilograms. That's a good size ship. Okay. So we know F equals ma, good old Newton, right? We're dealing with the mass of a ship. We're dealing with the acceleration we want to obtain. So F equals ma, yay. So let's figure out what the force got to be. So a 10 to the third kilograms, 0.01 meters per second squared, that's going to be 100 newtons. So I can get 100 newtons of force. All right, all I need to get is 100 newtons of force. Okay? That's half my weight, roughly. No. That's a tenth of my weight, something like that. Okay? It's 25 pounds-ish, 22 pounds would be, because a quarter of a newton, or a quarter pound is 1 newton. Anyways, meanwhile, back to the wrench. Radiation pressure, must be dealing with radiation pressure. And so if I bust out that radiation pressure equation, force per unit area, which that force will be the power, or this, it also equals this relationship, which is just I over c, speed of light. Now there's another way to look at this that I think might be a little better and takes us back to a first semester topic. It is the case that power in general is force times speed. That's generally true. Okay? And what that means is that if I'm dealing with the speed of light, then in our case we're dealing with force times speed of light. Well, that means force is going to be power over c, and power is equal to intensity times area over c, and that means that area is going to be CF over I, okay? Which I'd also get that from the blue stuff, okay? Area is going to be CF over I. So what I wrote in blue is equation hunting from textbooks. What I wrote in black is going back to the basics and applying it to this context, which I think is superior. Okay, but you have both that are effective. They both land in the same spot, which will lead you to the truth. All right, speed of light is 3 times 10 to the 8 meters per second. This force we're dealing with, or that is needed for the acceleration for that mass, is 100 newtons. We're 1,300 watts per meter is the intensity. Watts per meter squared, rather. And so that means the area required, drum roll please, 2.3 times 10 to the 7th square meters. Okay. 23 million square meters of solar sail, which sounds infeasible, but what if it were a square, okay, then our width of that square would just be the square root of our area, which would be roughly 4.8 kilometers, which is about 3 miles. So, I mean, you could roll it out, it's not impossible. It's practically impossible given what we have now. But I mean, you've seen things where they, this living thing and it folds out and it folds out again and then it extends out. It's totally possible that robots and whatnot could fold out a bunch of small versions and then link them all up out there in space. It's just a matter of, can we afford to build that? And can we afford to throw all that up in space? Well, right now that would be quite an undertaking, but all of it's possible. Just need to get a lot of rolls of solar panel up there and stretch them out. Or what if you can, what would be easier probably, and this is probably the kind of thing that'll happen in the future, is you'll extend the support mechanism or build it in space with robots and then 3D print your solar panels. that's easier than bringing fully assembled things into space. Okay? And probably, like going to Mars, there's probably several years of robots doing work like digging up dirt, melting it and making solar silicon so that they can build solar panels so that there can be power. Digging up dirt and rock so they can make cement and build structures. You know, so there'll be robots that'll have to go and do stuff because they don't need food, they just need to power up. So you send robots with enough solar panels and robots that can make more robots and more solar panels. Robots that are there to make more robot parts. I mean, that's the way it's going to start because I don't think we can afford to send a bunch of people. It's dangerous and they'll die. Lots of them will die if they don't have nice accommodations when they get there. All right, so just watch the movies. All right, so 1/100th of a meter per second.
It's like 50 million meters per second.
Yes. So, but it keeps building. It's a constant acceleration, so it keeps building up speed.
Right, so when you get there, you're freaking fly.
You're going to be, well, yeah, you'll want to slow down. You want to pull the sail in a little bit or something, and let go of the sail, do something, you know. If you hit it just right, it'll just coat your whole area, and you have a new solar panel on the ground there on Mars. Anyways, if it doesn't break into a billion pieces. All right. Suppose that researchers want to place a satellite above the north pole of the sun, at a suitable distance, I'm sure, stationary with respect to the sun, which means it's still moving really fast because the whole solar system's moving really fast, to study its long-term rotational characteristics. Scientists wonder about these things because they have no life. All right. Satellite, it's not true, but they can't dance. The satellite will have a totally reflecting solar sail. So that means totally reflecting means a double of that eye perceive thing if we're doing power. And it'll be located 1.5 times 10 to the 11th meters, so 200 billion meters roughly from the center of the sun. The intensity of sunlight at that distance is a known quantity apparently. Solar cell's perpendicular to this imaginary line coming out from the center to the satellite. Satellite's 100 kilograms. What's the required area of this solar sail for this thing? Because it needs to power up to do all these measurements and beam it back to Earth. So once again, we need to keep gravity, the force of gravity, in check with the force of the radiation pressure. If it's going to be stationary, that has to be true. So I don't want to, place a satellite above the North Pole of the Sun stationary. That's why we write this. The problem didn't tell you have a force balance, or it didn't tell you directly. You have to learn how to detect that that's a necessity, and that this is a right starting point, because we already learned what will radiation pressure do. It'll push things away. So I want to have a solar cell, or I want it to be at this location for some other reason. It's a constraint that was put on me. And either I know why it's there or I don't. Probably it's a constraint so that the dang satellite can function and not melt. Probably it's a constraint so that the satellite can send and receive information over radio wave without interference from the sun, because the sun's one huge magnetic electric storm. Okay? It's really pretty amazing. It does weird stuff because the electromagnetism of stars is really bizarre. Very difficult stuff. All right. So this is a great starting point. Okay? To know that this is true, and so that means I can write Newton's law of gravity, which will be big M little m for the satellite, big M for the sun. That's a nice, well-oiled machine. And the radiation force is going to be this little equation that we've actually used once or twice already. So I'm sort of cheating and bringing that out. All right. So now we have this really great balance, and I think we know everything but area. Kind of nice. So let's see. Area will equal Newton's gravity constant, little m big M, over 2ID squared. So let's see. Newton's constant is a 6.67 times 10 to the minus 11th and a bunch of units. The speed of light is 3 times 10 to the 8 meters per second. I'll skip the units because everything's the right kind. Mass of the ship was 100, or the satellite was 100 kilograms. So it's a little one. It's a wee little. Basically, yeah, that's a really small ship. The mass of the sun is not so wee. 10 to the 30th kilograms, roughly. And then we have double the intensity, which we were given as 1400 watts per square meter, and then that distance, 1.5 times 10 to the 11th meters. So that means the area of this puppy needs to be 6.32 times 10 to the 4th square meters, or 63,000 square meters. This is feasible if we knew how to manage that, and here's why. If circular, okay, then the radius is just going to be the square root of the area we know over pi. Pi r squared. Solve it for r squared, take a square root. And if you do all the plugging and chugging, it's only 142 meters radius. Okay? So that, if it was a thin enough material, it would work. There is a material, it's called Kepton or something like that. And you could make this if it was about, I want to say 8 to 10 micrometers thick. And the problem is we just don't have the technology to manufacture it that thin. But it's these are the kinds of things that they work on at, Sandia Labs or Oak Ridge National Labs, or in various companies that manufacture stuff for NASA and whatnot. I guarantee you that who are the two people that are trying to get to space? The Tesla dude and the Branson dude, right? There's a couple of big billionaires that they're working on. They got people working on this. They'll probably figure it out before the government does, because money and non-government procedures. Lack of government stupidity. All right. So anyway, so that's how this stuff would apply, and I picked these problems because these are real world kinds of considerations. Somebody somewhere is actually working on solutions to these problems, and somebody did math like this that directs them to what they're doing now or what they're trying to do now. Right? So.